everyone. I'm Preston.
I'm Max. I'm Jacob.
Our process was electroplating. So just a quick agenda. We're going to do a quick overview of what electroplating is, how it kind of works, and then the description of like how the process works in like in a factory, and the methodology, and then we'll do pros and cons, and insights and reflections. So here's some quick reasons on why electroplating is an essential process. Basically, electroplating involves putting a thin metal layer on a conductive object with using an electric current. It's widely used in many industries, especially electronics, jewelry, aerospace, and automotive. It enhances corrosion resistance, improves the aesthetic appeal. It's a very smooth layer of metal on top, and increases durability. And it's one of the only processes that creates this very thin metallic layer through the entirety of a workpiece, creating a metallurgic bond between the workpiece and the new material. So the key objective of this presentation is to help you guys understand how it works. And to do that, I'm going to go over the chemistry of how it works. So over here on the right, there's this example. The liquid in this is a metal salt solution, right? And the object that wants to be coated in the metal layer is given a negative current. It's acting as a negative electrode, a cathode. And when a current is supplied through the system, the copper ions or the metal ions, it depends on the solution, but they fall out of the solution and attach themselves onto the negative current, the cathode. And then the sulfate ions, in this specific example, because that's copper sulfate, they attach themselves onto the positive electrode. And that's how you can get a very thin layer all over the piece.
Alright, so just take a more broad overview of the manufacturing process. We created this step-by-step workflow of how electroplating is done, mostly in the industrial setting. Steps 1 through 3 is kind of like your pre-processing phase. So when you're disassembling the part, that just makes sure that if you have multiple parts that go together, in the graph it's gears and stuff. This will just ensure when you're plating it, all surfaces are evenly coated. And then stripping and polishing they can kind of go together, where you're basically just removing any layers that would prevent a smooth finish from electroplating. Going on, steps 4 through 6 is where the process is actually done, where steps 4, you're basically just cleaning the surface, making sure that any coatings will adhere to your cathode that you wish to adhere. And then step 5 is going to be your setup period. This is where you just make sure you have everything, most importantly your electrical current, where without it you won't be able to actually electroplate. And then afterwards you have your plate bath, and this is where you have your cathode, anode, and then your electrolyte solution, all in a bath or other system, which we'll talk about later, and where you actually oxidize the anode, and it'll dissolve the electrolytes onto the cathode to create your smooth finish. And then afterward, it's kind of your post-processing, so steps 7 through 9. This is where you just make sure that you have a smooth, even finish. And then step 8 is basically just your waste disposal. This is not every single process of manufacturing type methods. Don't really use this, but we'll see later that it is an important step for one of them. And then finally, you have your finished product. Going more into some technical details, there are many different anodes you could choose to electroplate with. They have different applications and characteristics to them, so depending on what you want to make. So for example, copper is a pretty widely used ones for your electrical conductors, PCB boards, and plumbing. Other ones of note are gold, pretty commonly used for electronics, jewelry, aerospace. And then just to highlight one more, platinum, very useful for chemical equipment and electronics. Some of the main manufacturing processes that are being used right now are up here above. Going over to the northwest corner, we have barrel plating, and this is your highest production rate, but it's mostly used for small items, so your screws, nuts, and bolts. This is done by rotating a barrel filled with your electrolyte solution, applying a current to it, and keep on rotating. This ensures that all the parts inside of it kind of get an even coating. This is not suitable for large delicate objects But because of this, it's very cost effective for high volume products. To the right of it is rack plating, and then this is suitable for your large and detailed work pieces where it is submerged into an electrolyte bath from a rack. This process is a bit time consuming, but it is great for high precision and quality, and you'll see this mostly used in like the aerospace and automotive where that's essential. Going on from that is electroless plating, and this is the one where like that step 8 comes to mind where you need to keep management of waste management. This is because that no external electrical current is required for this. It's mostly used for like your plastics and ceramics. Instead, it uses a really like powerful chemical solution to get the process done, which chances are that that chemical solution will be more toxic than others, so you have to be management of that. Going on from there, we have continuous plating, and this is like designed for like high-speed plating of like long uniform parts like wires and tubes. This is pretty much similar to rack plating where workpieces move continuously through a plating path. Yep, ideal for like simple repetitive shapes. And then lastly is brush plating, and this is pretty much like your quality assurance method where if you take any other process on here and it's like missing a spot, brush plating will just like make sure you get that spot up, cover it up. And then going on from there, we're going to talk about some advantages.
Yeah, so some of the advantages of electroplating over other coating processes. Thickness control, because it's submerged in a liquid, it can evenly coat all throughout the piece, which is very helpful. It can be cost effective sometimes, especially when you have these processes where it acts continuously, because it can be cheaper than other metal coating techniques, and also it can be quicker sometimes, which can decrease cost because you're increasing your throughput. The electrical conductivity can be an advantage sometimes, especially in electronics, as you can get good contact points. And then the corrosion resistance, as the metal layer, especially with some metals, it's specifically with nickel and chromium, the corrosion resistance can be really helpful. Now some of the limitations, as we already talked about, there are environmental concerns because it uses toxic heavy metal solutions and hazardous chemicals, which can pose a threat to the environment. And then second limitation is also health risks for the same reason. A lot of these metal solutions can pose a risk to employees around them because they include metals such as lead, cadmium, and chromium. Quality control and assurance. So because of the complexity of the chemical bath, and if you're using the same chemical bath, as you use it, when metal ions fall out of solution, the concentration of the solution can decrease, and that can mess up the layering effect. And if you need a specific layer depth, it can mess that up. So sometimes quality control and assurance, if you haven't done the calculations for it properly, can be messed up. And then there's a high capital cost, as the machinery to do electroplating can be very costly upfront, which limits smaller operators.
And then going into advancements in electroplating technology, specifically over the past decade, we'll start off the technological advancements. First up is automation. We've seen AI and machine vision for real-time defect detection come into play, which is huge. And then also for sustainability, they shifted from a toxic hexavalent chromium to a safer trivalent chromium due to the EU's REACH regulations. And then going into materials and techniques, alloy coatings are huge for enhanced corrosion resistance and aesthetics. And then pulse plating, also alternating current for uniform dense coatings, reducing hydrogen embrittlement, and then electroless plating as well, which is uniform deposition on non-conductive surfaces. And then for just our overall group takeaways and future potential that we gained from this project, some improvements we saw was pulse plating and the automation that's going to lead to reduced waste and energy. And then they're really focusing on trying to get more green processes, because this does, mentioned right here in challenges, it has a pretty big environmental footprint and can really cause issues there. It also has high costs, like Preston mentioned before. And then just in terms of future potential that they're working on, integration with 3D printing. They're trying to electroplate 3D printed parts, which would be better cost effective. And then just continuing to really enhance AI-driven automation as well. That's pretty big in every aspect in our world now, but electroplating's doing that as well.
Thank you. Any
Thank you.
questions?
Good job, good job. So assume you are an engineer working for an electroplating company. How do you imagine this engineer's job duty will be like? What do they do?
Like on a day-to-day?
Yeah.
Probably, with the, like I mentioned with the chemical baths,
Yeah.
making sure that the solution is proper. And then probably just quality assurance, like making sure that the pieces are properly coated, things like that.
What are the common defects associated with quality issues?
Like a lot of them, like just based off like the part itself, you could like miss a part on like the electroplating. So like for example, like aerospace, you have to be really precise with that stuff. It's like there's just like regulations for that. And when you like have like a small defect on there, you gotta like cover that up and just fix it. It just takes time. So that's like a pretty common defect from this process. Other than that, like I would say too is just like making sure that you're not like overdoing the electrical current. Because if you do that, you're just gonna like not get an even distribution. Because if you charge it too much, it'll come too centralized. So you'll have like, if you imagine like a square piece, it'd be really electroplated, concentrated, and like the center of the square versus like the outside of the square.
Yeah. For this part, how does AI can be integrated? You know, what is it more on the process side or the quality side?
Yeah, so I mentioned it in there, AI for real-time defects. So if there's anything wrong with the electroplating, kind of like that, if there is a defect or something, that's when AI can come in and like alert like the manufacturing engineer or anyone doing it, and it can actually like stop the process or fix it.
Okay, so it's mainly like a machine vision based.
Mm-hmm.
Okay.
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 Awesome.
Good
Thank
job.
you.
Good job.